Uh, Thanks. So this is joint work with my supervisors, Nils, and Andreas. And I realized while walking here this morning that we messed up the title. The word graded should be in here somewhere, I think. So you imagine that it's in some appropriate location in the title. So 3 years ago, me and Andreas wrote an abstract for types. I couldn't go, but Andreas presented it, which was about this AGDA formalization of graded type theory, where you have some kind of type system where you somehow count how many times variables are being used. We see some example of graded types in previous talks as well. We focus mainly on erasure, so keeping track of things that are unused when you run the program. But we sort of had the intent that the same system should be applicable to, for instance, linear types or affine types or other kinds of type systems where we keep track of how many times things are used. I'm not going to tell you exactly how this works, but the main idea is sort of that we have this triangle kind of typing judgment, which is for counting. It assigns some context gamma, telling us how many times the free variables of the term are being used. And we use some kind of addition and multiplication to count up how many times variables are used. So there is some simple example here. These two variables, Z and W, are used once by themselves, kind of. And we have this function taking two variables. The first one is used twice, the second one is unused, and we add the first variable together with self. So at least if we believe that plus uses its arguments once, this seems to make sense. Y is clearly unused and X should be used twice. And when we count this up with this rule for application where we add resources and scale them, we end up sort of counting the Z variable as being used twice because that's the one we apply first. And the second variable ends up being considered unused because we scale it by 0 in that case. Right, so these grades are technically some elements of some simmering, but for the purpose of what I'm saying now, you can think of them as sort of sets of natural numbers, kind of representing some allowed amount of uses. And this is sort of more formally expressed by this subsumption rule, allowing us to switch the context given some partial order of these grades. But in terms of the set interpretation, if here X is used exactly once, we can think of it as being used either 0 or 1 time. Because sort of we think of the grade that this set represents as being a smaller grade than the singleton one set. But what we're doing now is sort of thinking of how to extend this to handle recursion. More specifically, we're thinking about just natural numbers for now with Natric, the eliminator for natural numbers. But we think, at least I think, that the same ideas should be applicable for other recursive types as well. But that's for future work. So before we look at the actual Natric, plus is more concrete and simpler example. We've already seen it. Torsten showed it a few days ago, but this time it's in AGDA. And well, clearly in the 0 case, the first argument M ends up being used exactly once. But sort of in the second case, it's not as clear because to figure out how many times M is used here, we need to figure out how many times it's used by plus. And that is sort of the whole question that we're trying to solve. So we might guess from the 0 case that it's used once, and then look at the successor case and see that, yeah, if plus uses M once, then this all works out, kind of. Alternatively, we can consider sort of all the possibilities, however many times this plus function will be unfolded when we evaluate it. If we evaluate it 0 times, just looking at the base case, we get M. unfolding it once gives us this extra m, and so on. And so it seems like the m is actually being used exactly once in all cases. The other argument is perhaps not as clear to see here because it sort of seems like it disappears when you do this. But we also need to keep in mind that we actually do the pattern match on the end. So that also ends up being used once. And yeah, so the sort of grade we would assign to both of these arguments in this case would be the one corresponding to this singleton set one. Both of these arguments are used exactly one time when we run them, or we would expect them to anyway. We can do the similar thing for multiplication. This time m seems to be unused in the 0 case, but sort of if we were to guess that 0 is the right thing, we did in the plus, then, well, it doesn't work out because here m is used once plus, well, we guessed 0 times, so 1 plus 0 is 1, but that was not the same as our initial guess. Unfolding it, we this time get 0 times in the base case, then 1 time, and then 2 times, and so on. So here it depends, however many times we end up unfolding it. So sort of the value of n is the number of times m is going to be used. So the best thing we can really do here is to take the grade corresponding to any number of uses. We can't really say anything. For the other argument that again sort of disappears when you do this unfolding, we just have the pattern match. So that one is actually linear. Okay, so now you probably have some sort of idea of how we can think of recursive functions and count variables. So let's do the interesting metric case. This is not actual AGDA code anymore, just looks mostly like it. So metric takes 3 arguments. The 0 case instead, successor case, a function taking a natural number, and the recursive call. And I annotated these with some grades, P and R, telling us how many times these 2 arguments are going to be used. And this is the part that's not in AGDA, not yet anyway. And then, of course, it takes the natural number that we do the recursion over. And yeah, it's defined like this. And again, the problem here is that in the successor case, we have this recursive call where we need to already know the answer in order to say how many times things are going to be used. But the same strategy that I showed for addition multiplication, we can do for NATREC, considering sort of all the possibilities of this number n. And I'm now looking at sort of figuring out how many times this number n is being used. So in the 0 case, again, it looks like it disappears, but we still have the pattern match to keep in mind. So then the natural number is used once. When it's 1, we sort of apply the predecessor 1, 0, to s, and then the recursive call, which was said. Now, we said that this function s uses the predecessor p times. So this is 0. This is essentially the number. Well, it's the predecessor of the number, but essentially the same thing. So then we get sort of p uses of the natural number from there. And we also have that the recursive call is used r times. And in the recursive call, we said that the natural number was used once. So we get an additional r uses from there. You can continue doing this unfolding more and more times, and each time the same sort of pattern will apply. First get p uses from applying the predecessor, and then r times however many uses we had in the previous step. So in the second case, we get p plus r times p plus r. And yeah, again, sort of the grade we would need to assign is then the one corresponding to the set of all of these infinite number of numbers or grades that we get from this. So in particular, if we were interested in figuring out when is this natural number used linearly or exactly once, we would need all of the elements in this set to be 1, which maybe it's not super obvious, but it's when one of P and R is 0 and the other one is 1. So either the number can be used, the predecessor can be used, or the recursive call can be used exactly once in either case. So sort of going back to sort of the actual way we express this with this subsumption rule, what we really do assign is the grade that's the greatest lower bound of all of these grades that we have in this set interpretation. And we can do sort of a similar kind of analysis for how many times the Z and S arguments are being used. I'm not going to show you, but it's essentially to do the same kind of unfolding. Then, of course, we need to ask the question, was this analysis correct? Or it seemed reasonable to me, but maybe it's completely wrong. The answer is yes, otherwise I wouldn't be standing here. We have